So first of all, we need to show that x minus 1 equals cos x has only one root, meaning only one solution. So that means if we draw the graph of x minus 1 and the graph of cos x, that should suffice. So if we draw ourselves a nice trigonometric curve, then if that's cos x, then we can put in an axis here, and the other axis goes pretty much through the middle there. And then it's worth putting a little dotted line along here, because that shows us where minus 1 is. And the line x minus 1, y equals x minus 1, oh, we better label that as well. So that's y equals cos x. The line y equals x minus 1 has a gradient of 1 and goes through minus 1 as its intercept, which means it will go through 1 on there. And we also know that that's pi by 2, and it's worth marking that on because it makes clear that this crosses to the left. And then we'll put y equals x minus 1 on that, and I think that's got all the information we need. It is important that we show that it's to the left of pi by 2. If we imagine a line going through minus 1 through pi by 2, or to the right of pi by 2, at some point one of those lines is going to hit the curve down here. So if we know it's to the left of pi by 2, we know for certain that the only root is here in green. For the next part of the question, the Newton-Raphson method works when we're looking for a root, meaning a value that makes the equation equal to 0. So, because we have x minus 1 equals cos x, then what we do is we turn it into x minus 1 minus cos x equals 0. And so this is our function of x. Now the Newton-Raphson formula looks like this. So if we already have a root xn, we get an improved root xn plus 1 by plugging xn into this formula. Now you've probably seen this before, but it's still worth brushing up on so you understand what's going on. So if we have some function and we have an approximation here, call that xn, to the root which is here, then if we draw the tangent on, so that will go down like that, then you can see that we get a better approximation, which we'll call the x value xn plus 1. So, how does this formula come out of that? Well, this is the curve f. This red line is the tangent to f. Now, what that means is that if we draw a little right-angled triangle here, then we can say that's the change in y and that's a change in x. But actually, because the tangent is the gradient at the point above xn, then we can say that f dashed of xn equals the change in y over the change in x for the tangent line, the red line. Now, we know that delta y is the function f applied to the point xn, and delta x is equal to xn take away xn plus 1. So if we substitute those into this f dashed of xn that we have up here, then we get f dashed of xn equals f of xn over xn minus xn plus 1. Cross multiply gives us xn minus xn plus 1 equals f of xn over f dashed of xn, and we can then add the xn plus 1 or subtract the f of xn over f dashed of xn, and we end up with xn plus 1 equals xn minus f of xn over f dashed of xn as per the formula. Anyway, we now have our formula, which we had already, but now you know where it comes from. And to use the formula we need f of x. So f of x, as noted before, is x take away 1 take away cos x. So f dashed of x will be 1. Minus 1 differentiates to nothing. Cos x differentiates to minus sin x, so we get 1 plus sin x. So that means our xn plus 1 equals xn minus xn minus 1 minus cos of xn divided by 1 plus sine x of n. Xn. So that's a bit of a handful to enter into a calculator, so you will want to use a little trick, which is we're told to use x0 equals 1, then we do 1 equals, and then we enter this. When we press equals for that, we get this answer here, which is our x1. So x1 equals 1.293470993. We press equals again and we get x2 equals 1.283435773. We press equals again and x3 comes out at 1.283428742, and we can see now that to two decimal places, which is what we're asked for, we have that already. The next two decimal places after that are also matching, so we could be pretty confident of 1.28, but because we can easily enough by pressing equals again get the next one, it's worth doing that as a check just to be sure, and it turns out that actually that matches all the way down, so we can be really confident of our answer. So we better write that in, and so we can say that x equals 1.282 dp or 2pd. One thing we must be careful of is avoiding this situation. Now, this is the display after the first one equals and then the formula equals, and you can see that we have a quite different answer, and you will probably be thinking, degrees and radians. You must make sure when using this method that your calculator is in radians, and in fact whenever you're using calculus, and as we've seen from the derivation of the formula, we are using calculus. You can see in the formula we've got f dashed, so we're differentiating. You always need to put your calculator into radians. I thought it'd be nice to look at Newton-Raphson with the actual graphs, see what's happening. So we've got our function in here, and we've got our starting point at 1. So with our starting point at 1, we can then get our f of x, 0, which is obviously on the curve, and then we can plot our tangent there, which goes like that. And you can see that with the first one we're getting quite close to our root here. So if we zoom in, then we can see we're at that first value there, and that is our second point. And then we need to plot that up onto the curve, so that's our f of x1, and then we do the tangent, and this time at that zoom it's almost exactly the same as the function. It just starts to stray a bit down the bottom there. If we zoom in, it looks very much the same. But let's put our next point on, and let's see how far we have to zoom to separate the tangent from the curve. We're having to get very close in, and so you can see why the x1, x2, x3 converge on several decimal places so quickly. We'll just have a look at the next one. So there's our f of x2, there's our tangent, and there's our next point, and again we've got to zoom right in. In fact, I wonder if Geogebra can cope with the amount of zoom we're going to have to do to get to separating the tangent from the curve. I find this quite mesmeric. I hope you enjoy it too. Well, there's the tangent, but the curve appears to have disappeared, so it possibly is struggling to cope with this. But anyway, you can see how quickly that converges. So if we go right back out again, I didn't realise quite how far I'd zoomed in. Oh, here comes our next tangent. And our next one. And there's our x1 coming in, and there's finally our x0 coming back. So we'll zoom in some further so we can see the curve a bit more. And in this question you're given your starting point. Now maybe they'll always do that in the exam, maybe not. But if they don't give you the starting number, what they'll likely do is give you some way of estimating it so that you get a sensible starting point, because if you don't use the right sort of starting point, Newton-Raphson doesn't work very well, or even at all. And in fact, if we move x0 around, you can see that in the vicinity of the point, and in fact if I put the next estimates on, just zoom in a bit so we can see them separated off, they're all, although they're showing, as we can see here, they're all pretty much on the same point, so that's very definitely converging nicely. Now if however we go too far away, then we can see it's still going to converge there, it looks like, but at some point it starts to go a bit weird, and you'll probably have guessed it's something to do with what's going on here with the curve. We've got some sort of turning point thing going on, But here we can see that the first estimate is the x0 is here, then it goes to x1, and it goes back to a similar place, but then it's widening out. Then it gets to x4, and x5 is now off the screen. In fact, I could stick the tangents in, and you can see that it's just getting a bit crazy. So, if we go further still, it's not going to work at all. Go back down through 1 and we can see that there we're in the region where it does converge, but then if we go away from 1, it's still working okay. So if they'd given you 0.5 as a start, it would have worked okay, but now we're approaching this turning position here, so we think it's going to go wrong again, I think, and sure enough, whoa, it does go wrong. So, key thing about Newton-Raphson, your first estimate has to be reasonably close to the actual root. What reasonable means depends on the type of function it is, but if you're given a question without the starting point, they will give you some way towards it. And the other thing is, by putting the formula into your calculator using the answer button, then you can see if the answers are starting to jig about too much and not converge, and then that tells you that you've used the wrong starting point, so you need to have a look at that.